Now that we've talked a little bit about waves, we will talk about sound. So, sound waves are able to propagate by, at least for human hearing, are able to propagate through the air. So, the unique thing about sound when compared to, say, something like light is that sound requires a medium in order for it to propagate. So, for example, the light from the sun is able to propagate through space, even though space is a vacuum. And there's no particles in between us and the sun that light wave can travel through, basically. However, sound needs a medium to travel through. So, for human hearing, that medium is the air around us. The individual particles of the air will oscillate uh, in the direction of the uh, sound waves travel. But it turns out that sound d- is able to propagate through things other than just air. So the speed of sound, so how fast that sound wave is able to propagate, will depend on two main factors. So the first being the medium of travel. So, for example, the speed of sound in air is different than the speed of sound through water. And the other thing that the speed of sound will depend on is the temperature of the medium. So, the equation for the velocity of, or the speed of sound, with respect to temperature is this equation. So this 331, this is the speed of sound, and this capital T is your temperature. But when you use it in this formula, this needs to be temperature in Kelvin. And this factor of 273 is basically this 331 for the speed of sound. This is the speed of sound at 273 Kelvin. So if you have a temperature higher than 273, then your speed of sound will increase. But if you have a temperature lower than 273, then the speed of sound will decrease. So the speed of sound will increase with increasing temperature. And we talked about the medium of travel. So sound can travel in gases, liquids, and solids. And so you can imagine something like water. So water can exist in a gas form, in a liquid form, or in a solid form. And so the speed of sound will change even though it's the same H2O molecule. The state of matter, whether it's a gas, a liquid, or a solid, will change the speed of travel through that uh, H2O, and also the temperature of the H2O will change the speed of sound. So even if you had still water in H2O in a liquid phase, If the liquid was hotter, then the speed of sound will be greater than in a container of H2O with a lower temperature. So the speed of sound depends on the medium and the temperature of the medium. And once you have the speed of sound or the velocity, we can relate that to the frequency and the wavelength of that wave. So this is the speed or velocity. This is the frequency. And this is the wavelength. So if we think back to our picture of a wave, this is time and this is position. And so that's the period of the wave. And the frequency is just the inverse of the period. Then if you look at a position versus position graph, the distance from peak to peak on a position graph would be your wavelength. So the wavelength and the frequency are just two different ways to measure characteristics about the wave. And it turns out when you multiply them together, you'll get the velocity of the wave. So typically what we'll do, let's say the speed of sound was the 331 meters per second that we had previously. Let's say we know that the frequency of a given sound wave is 120 hertz, and this hertz unit is the same as 120 basically cycles of that wave per second, so 1/second. Given those two values, we can calculate what the wavelength of that wave must be. So we rearrange this equation. It's all for lambda, so we divide the velocity by the frequency. So we're doing 331 divided by 120. And if we want to look at the units, this is meters per second, and this is 1/second. So you see that your seconds units cancel, and you're just left with units of meters. So if we take 331, so when you plug this into your calculator, you calculate the wavelength to be 2.76 meters. The intensity of a sound wave is another way of talking about its loudness. So the intensity represent with the capital letter I, and that is equal to the power divided by the area. So this is the power being delivered by the wave, and this is the area, the surface area of whatever object is receiving that wave, or whatever area the wave is passing through. So remember, power is the energy per time. And so you can think of the intensity as the energy per time per area. So if we want to think about sound waves, the part of our body that is hearing the sound wave or that is processing the sound wave is our eardrum. And so that has a very small area. And we'll see in a moment how much intensity it actually takes for our ear to be able to discern or detect a sound. But now we'll talk about another definition for the intensity, and this will shed some more light on what a sound wave actually is. So another definition for the intensity is the square of a pressure differential or pressure variation divided by 2 times the density times the velocity. So this delta P is a pressure variation. We'll come back to that in a second. This is the density. This is the Greek letter rho. And so this is the density of whatever medium you're propagating through, whether that's water or air or some solid. And then this v is the velocity or the speed of sound. And we saw how that depends on the medium and on the temperature. Okay, so if we come back to this pressure variation, this delta P is just an average pressure. So we take the max pressure of our sound wave, divide or subtract the minimum pressure, and then divide by 2. So what sound actually is, if you have some object that generates a sound, whether that's you striking an object or your vocal cords starting to vibrate, that once the object or your vocal cords vibrate, they are actually starting to vibrate the air around them as well. And so that air will push against the air molecules next to it. And remember, the sound waves are a longitudinal wave. And so as uh, those air molecules hit the ones next to it, the sound wave propagates. And we can think about that sound wave propagating as a pressure wave. So when my vocal cords vibrate, they are vibrating the nearby air molecules. Those air molecules bump into the ones next to them, and those molecules bump into the one next to them, and so on until the air molecules next to your eardrum vibrate and hit your eardrum, and that causes you to hear a sound. And so what sound really is a pressure wave propagating, in this case, through air. And so the intensity, we can define that by thinking about the pressure of the wave as it propagates through space. And next we'll talk about what actual values we have for the intensity for things like um, the minimum threshold in order for a human to be able to hear something, and then also for louder things like human conversation or even how loud a sound needs to be in order to rupture your eardrum. So we can measure the intensity of sound waves using the units for power over area. So the units for power are in watts, and the unit for area is meters squared. But we can simplify this a little bit. So watts are kilogram meter squared per second squared per second. So you can see you could get your meters to cancel and you would get kilogram seconds cubed. But it turns out when you use these units, the intensity that humans can just barely hear, we'll call I0, is a very small number, 10 to the minus 12 watts per meter squared. So this is the lower range of human hearing. And so it's not always convenient to use numbers with these really big, or in this case, a really small exponent. And so instead, we devise a new way of thinking about sound and its loudness, which with something called the decibel. And that will be kind of units of dB. And so the decibel is defined like this. You take 10 times the log base 10 of whatever sound intensity you're interested in and divide it by that lowest intensity sound that humans are able to hear. And so, just to give a sense of scale, so 0 decibels is the equivalent of this lower range of human hearing. So, this is threshold of human hearing. "60 decibels is about the level for a conversation, so two people talking. 100 decibels would be the sound of a factory, and 160 decibels is when your eardrums would rupture. So there could be sounds louder than that, but if a human ear were exposed to that sound, it would just break your ear and its ability to hear things. Okay, so let's investigate this. So this was our equation for how to calculate the loudness of a sound using decibels. So first, if you're not familiar with this log base 10, what a logarithm does so what this logarithm is asking is what power do I need to raise 10 to in order to equal A. So for example, if A were to equal 100, log base 10 of 100 would equal 2. And that's because if I raise 10 to the second power, I get 100. And it's even easier to see if I make A equal to 1,000 or 10 to the 3, log base 10 of 10 to the 3 is just going to equal the exponent of 10, which is 3. So you can have logarithms, you could have log base 2, and this is common for computers. So if I make this 16, this is asking what power do I need to raise 2 to in order to get 16. So we'll remember that 16 is actually 2 to the 4th. And so I need to raise 2 to the power of 4 in order to get 16, which was the thing inside of our logarithm. So now let's apply this understanding of logarithms to this equation for the decibel level. So with this equation, and remember let's compare the 60 decibels for a normal conversation to the 100 decibels for a loud factory. And our baseline was the 0 decibels for kind of the lower limit of human hearing. And we said that corresponded to I0 of 10 to the minus 12 watts per meter squared. So let's see what the decibel level, or we know the decibel level is 60 for human hearing, and let's see what that corresponds to in terms of the intensity. Okay. In order to do that, we have to basically undo a logarithm. So first we'll divide the 10 to the other side. And now we have 6. To undo a logarithm, you need to do 10 to the power of both sides. So 10 to the 6 equals 10 log base 10 of I over I0. So 10 to the 6 we'll just leave by itself. 10 to the log base 10 will cancel, and all that you're left with is what was inside the logarithm. So solving this for the intensity, we get 10 to the 6 times I0. I0 was 10 to the minus 12. And so 10 to the 6 times 10 to the minus 12 is 10 to the minus 6 watts per meter squared. So that's the intensity of a 60 decibel conversation. So now let's do the same process for the 100 decibel factory. So 100 is our decibel level, 10 log base 10 I over I0. So 100 divided by 10 equals log base 10 I over I0. So 100 divided by 10 is 10. Now we do 10 to the power of both sides. Ten to the 10 equals, so 10 to the log base 10 cancels out. I over I0 is left. And so the intensity of a 100 decibel factory is 10 to the 10 times I0. So 10 to the 10 times 10 to the minus 12 leaves you with 10 to the minus 2 watts per meter squared. Okay, so let's explore what happens if, say, we want to compare two intensities of sound, I1 and I2, but maybe we don't have the actual values and we just want to say one sound is twice as intense as the other. What difference in decibel levels would that correspond to? So we could start with, say, for example, I0, which we said was 10 to the minus 12 watts per meter squared. And what if we want 2 times I0? So that would be 2 times 10 to the minus 12 watts per meter squared. We know the decibel level of I0 was 0 decibels. That was our baseline. So what are the decibel levels of 2 times I0? We can plug it into our formula, 10 log 10. So we're doing I2 over I1. In this case, that's 2 times I0 over I0. And then our I0s cancel, and we're just left with 2. So off the top of your head, you might not know uh, what the log of off the top of your head, you might not know what the log base 10 of 2 is. And so this is something that would be perfectly fine to plug into your calculator. And when you do plug it in, you would get something like 0.3. So remember, that's saying if I raise 10 to the 0.3 power, I should get 2. And you can verify that in your calculator if you want. And so what this is telling us is that the decibel level for a sound that's 2 times as loud as the minimum sound that we can hear, that should have a decibels level of 3 decibels. And so the difference between the 3 decibels and the 0 decibels is 3 decibels. The question now is, does that hold for any sound that's twice as loud as any other sound? So let's verify that. For normal human conversation, we said that the intensity for 60 decibels was 10 to the minus 6 watts per meter squared. So I'll just call that I2 or I1, and we want I2 to be twice I1, and so that would be 2 times 10 to the minus 6. Okay, so let's calculate the decibel levels for something that's 2 times 10 to the minus 6. And we have to divide that by the threshold for human hearing, 10 log 10 of 2 times 10 to the minus 6 divided by 10 to the minus 12. Okay, so 10 to the minus 6 divided by 10 to the minus 12 gives you 2 times 10 to the 6. Ten log 10 of, and so one of the cool properties of logarithms is that I can split this two things multiplied together inside of a logarithm by adding them together. So this is log of 2 plus log of 10 to the 6. So log of 2, we already said was 0.3. So we get 0.3 plus 10 to the 6 is 6. So this is 10 times 6.3. So that's 63 decibels. And we said the normal human conversation was 60 decibels. So 63 decibels minus 60 decibels gives us 3 decibels. So any sound that's 2 times as intense as If you want to find the difference in decibel level between any two sounds that are 2 times bigger than an initial sound, it's always going to be a difference of 3 decibels. Now, the actual intensity of the sound is a lot bigger, and this is the power of the logarithmic scale, is that you're really compressing a wide range of values. So we're going from 10 to the minus 12 as the kind of minimum for human hearing. And even for normal conversation, you're getting up to 10 to the minus 6 decibels. So that's 6 orders of magnitude that we've compressed into just a range of 60 decibels. So it really kind of puts it on a more human scale that's a bit easier to understand. Easier to understand a scale that goes from 0 to 100 rather than 10 to the minus 12 to 10 to the minus 6.